Hello everyone, welcome to another episode of Regressions. In today's video, we will be talking about support vector machines, a popular machine learning algorithm that can be used for classification or regression. But we'll focus mainly on classification in this video, since that's the most common use case for this algorithm. So let's dive right in. Here's the agenda for today's video. We'll be telling you what is a support vector machine or support vector classifier. We'll talk about how the SVMs work, how you can implement one in Python using sklearn. We'll talk about whether or not SVMs can be used for classification or regression. We'll talk about when you can use an SVM. We'll talk about using SVMs for multi-class classification, and we'll also touch on some ways you can improve your SVM model. So let's dive right in with discussing what is a support vector machine. A support vector machine is a supervised machine learning algorithm. It is a linear model. SVM works by finding the linear decision boundary between various classes that maximize the margin. We'll talk more about what margin is in the How the SVMs Work section. So now let's discuss how the SVMs work. SVMs are linear models. That means the boundary that separates various classes is a line. This is true in two-dimensional data. If you're dealing with three-dimensional data, it would be a plane instead of a line, and it would be a hyperplane in higher dimensional data. SVMs maximize the margin. Margin is the distance from the hyperplane to the nearest data point of each class. The goal of an SVM algorithm is to maximize the margin. Support vector machines often use L2 regularization in the model. However, traditional ridge regression uses alpha as the regularization term. SVMs use the term C as the regularization term. Another difference between SVMs and traditional lasso regressions is that in traditional lasso regressions, a higher alpha value means more regularization. In SVMs, a higher C value actually means less regularization. A low value for C attempts to classify every instance correctly, whereas a high value of C tries to adjust to the majority of data points. Earlier in the video, we defined an SVM as being linear. However, nonlinear SVMs are also possible and often desired if you are dealing with higher dimensional data. Linear SVMs are typically used in lower dimensional data sets. Let's bring in some visuals to further enhance your understanding of how SVMs work. So imagine we have some data, we have our y-axis and our x-axis, and we begin to populate our graph with some data points. So we have red circles representing one class and blue squares representing another class. So what an SVM will do applied to data like this is to find the linear decision boundary that best separates these classes and maximizes the margin. The SVM will learn the coefficient and weights that gives you the best line, and best here is defined as maximizing the margin. Remember, margin is the difference between your line, so in this example, the brown line, and the nearest data point of each of our classes. So the distance between the line and the red circle in one direction, and the distance between the line and the blue square in the other direction. Let's begin implementing our SVM algorithm. The first thing we'll do is import pandas with the alias PD, and then from sklearn model selection, we'll import train test split so we can train test split our data, which is what you should do every time you do machine learning. From sklearn, we'll import SVM, which is the function that we'll be using to implement our support vector machine. And then lastly, from sklearn, we'll import metrics, and you'll see why later. So now that our import statements are done, we need to import our data. We'll do data equals read CSV. I'll be using some mock income data, but you'll just have whatever data set you're using in here. Let's see what columns we have. So here we have certain fields such as the number of years of experience, and then we have some binary variables just implementing the level of education of our user or of our data. And then we have the person's age, and then our dependent variable here will be a binary indicating if they're wealthy or not. And that's what we'll be classifying new people as, wealthy or not wealthy. We'll be making that prediction. All right, so let's go ahead and put our independent variables in the variable called x. And we'll use the ilog function for that, which will give us the location of an index. We can pass the location of an index in, and then we can subset our data that way. And we'll pass in the colon first, which is just saying get all of the rows. So when you pass in the colon, the start and stop just brings in all of the data. So we're getting all of our rows. And we'll start at the first column and go until the last column, but not actually get the last column. So we'll start at index 0, and we'll stop at index -1. Then we'll do something similar to get our dependent variable. We'll get all the rows, and then we only want the last column there, so we'll just pass in -1. We'll run that. Now we can actually do our train text split. So we'll do x train, x test, y train, and y test equals train test split. And we'll just do x and y and run that. Now we'll actually build our model. So we'll just call this model, and that will be svm.svc. Make sure you capitalize the SVC. Between these parentheses, what we will put is kernel equals, and then in quotes, linear. Let's talk about what we just put between those parentheses. What we just did was specify the kernel for our model. Sometimes when using SVM, the model can't easily draw a decision boundary between classes. When this happens, the kernel will transpose our low-dimensional plane into a higher dimensional space where it can segment the classes. There are multiple kernels you can use, but we will use the linear kernel here. Another option could be the polynomial kernel, which can allow curved lines in the input space. So let's move on with our code. Now we have to fit our models. So we'll call model.fit, and we'll train on our x train and y train. And then we'll actually make some predictions. So we'll just call those y predictions as model.predict, and then we'll pass in x test. And then lastly, let's print the accuracy of our model. So we'll print accuracy, and then that will be metrics.accuracy score. And you'll pass in y test and y predictions. And you'll see our accuracy here actually isn't very good, but I'm just using some mock data to show you how to implement this algorithm, so let's not worry too much about the accuracy here. But that in a nutshell is how you implement a basic SVM in Python. We've discussed SVMs for classification in this video. However, we will also talk about support vector regression, or SVR for short. We won't implement this in Python as support vector machines are mostly used for classification, and we already have a video on a different regression method, ordinary least squares, on our channel, which you can go check out. When you use SVM for regression, it's called SVR. SVR works similarly to SVM in that it fits a hyperplane, but SVR differs in that it fits a tube around that hyperplane. This tube is determined by a parameter called epsilon. SVR works to fit as many data points inside the tube while reducing the slack. Slack here refers to the distance from the boundary of the tube to the points outside the tube. So you can see here the distance between the edges of this rectangle and our line. That would be epsilon, which the user can configure. And the distance between the boundary of the tube and the points outside the tube is called your slack. And so remember, you can use epsilon to configure essentially the width of this box. And you would want to be minimizing the distance between the edges of the box and the points outside of it. Support vector machines and other linear classification models are often used when you have a lot of features. Linear classifications tend to work well in high-dimensional spaces. The default regularization also comes in handy when preventing overfitting in high-dimensional spaces. SVMs also tend to work well when we have a high number of features relative to the number of data points we have. SVMs are not natively used for multi-class classification. However, that does not mean they can't be used for that. There are two potential ways you can do this. First, you can use the one versus one approach and create multiple SVM models where each model performs binary classification. With this approach, you'll have one model for each class. For example, if you want to classify a fruit as an apple, pear, or orange, then you have three models. One model will compare apples and pears, another will compare pears and oranges, and the last will compare apples and oranges. The second approach is the one versus rest approach. With this approach, you'll only train one model that will compare one class and the rest of the classes will be lumped together. In our example, for example, you could do apples versus all of the other fruits. I'll give you two ways you can improve your SVM model, and these aren't the only two ways, but they're two pretty easy ways that can give you pretty quick results. And that is experimenting with different values of C for your regularization, and you can also normalize or standardize your data. If you like this video, be sure to like, comment, and subscribe. When you subscribe, click the notification bell so you don't miss an upload, and also comment saying you subscribe, and I'll try to like or heart all the comments. We have a machine learning series on our page where you can check out other videos in our machine learning series, and we also have a lot of videos coming in the future about programming in Python, machine learning, artificial intelligence, cloud computing and Amazon Web Services, and physical computing using Raspberry Pis. So we have a lot of great tech content coming in the future, so make sure you subscribe so you don't miss any of it. Thanks for watching, and I'll see you in the next video.